All right, how about a woohoo? How about a woohoo? All right, that was a good one. All right, ready? Woohoo! Okay. Okay, great. That was a good one. Okay. Let's, greedy. Okay, we're going to finish up greedy. And then we're going to go on to dynamic programming. Anybody remember dynamic programming? Did you guys talk about it in 61A? Who saw it in 61A? Okay. Okay, so when you saw it in 61A, what did they call it? Memoization. So it's sort of like memoization. So in some sense, it's going to seem like a new topic, but it should also seem very similar. It should seem like recursion, okay? And basically, this notion, I mean, it's basic computer science. So we'll get into it more, but it's always a topic that's a little bit challenging, but in some sense it's challenging because recursion is a little bit challenging. It's just another chance to understand it better and understand it a little bit deeper, okay? So, okay, so here's a problem. It's called the set cover problem. So you can have items, B, which is some set of elements, just items, things, they could have numbers 1 to n, or you can think of them however you like. And you have sets, okay? And each set is a subset of these elements. So S1 might be the element 1, or S2 might be the element 1, 2, and 3, okay, and so on. Okay, there's subsets of the base set, yeah. Oh, okay. Okay? Okay. Okay, so let's try that again. There's set B, 1 through n. We have, this is part of the input. The input is a set of sets, okay? And what you want to do is cover the elements of the set. You want to find the fewest of these S sub i's that cover B, so that the union is equal to B, okay? So it may be that S1 contains the first element, and or the first 2 elements, the first half of the elements, and S2 contains the second half of the elements plus 1 element from the first element, and the union is still B, right? So it doesn't matter if there's repetitions. You just want to, the desired objective is to minimize the number of sets that you use in your solution. Okay? So one example is this, the items could be city blocks, and the sets could be possible cell phone tower locations. So you can say, if I buy this location on the top of the Empire State Building, I will hit all the blocks within 10 blocks of that. Okay? That will be the set of objects that tower covers, right? Does that make sense? Yeah, so each cell phone tower location covers some subset of the blocks. Okay? I mean, in that case, you have more structure on the sets, but it's clearly an instance of this problem, right? So your job is to buy cell phone tower locations. You want to buy the fewest you can. This is what this problem is modeling. Okay, so customers and walnut mark locations want to cover some subset of the customers. You know, that's another example of an application, right? You want to put down the fewest Walmart locations. I mean, obviously, in real life, these things have cost and et cetera. This is a simple version of these problems, but they're everywhere in some sense. Okay? This particular problem itself is everywhere. And variations can be solved with similar techniques that which we're talking about today. Okay, so another thing is job responsibilities. So maybe some of your employees can do Ruby and some can do Perl. You know Ruby? Does anybody know Ruby anymore? Is it gone? Yeah. I programmed a lot in Ruby, but now it's Python's better. So Python has better whatever. I don't know. People have arguments, but Python's one. So it's people with set of job capabilities. Maybe you want to hire a team to cover all the things the team needs to do. Okay. Factory items, touch screens, chips, cheap labor, and you want suppliers to cover all of these things. You know, these are all real problems. You know, I think GM has thousands of suppliers, for example. GM is General Motors, if you don't know. It used to be a big company, but now these companies like Instagram are bigger, so I don't really understand that. But yeah, okay, well, okay, choose. So here's I mean, here the greedy algorithm is really kind of obvious. You just pick the set that covers the largest number of locations, right? You pick the cell tower on top of the World Trade Center, or if that's one of your locations. So here, there's nothing subtle about what the greedy algorithm is at all. It's all just, well, I'm going to pick the set that covers the most of the elements. That's the first thing I'm going to do. Then I'm going to remove those elements. Now I'm going to look at all the sets that are remaining. I'm going to remove the elements in those sets that are already covered. So now I have a new problem, right? And I want to cover the remaining elements with the fewest number of sets, right? So I just repeat. Rinse, repeat, yeah. Do people get the rinse, repeat joke? Have you heard that? Rinse and repeat. Do they not say that in the lower division? Yeah. Okay, so you do, or where the rest of life. I guess you had life before the lower division. Okay, number of sets is the number of iterations of this algorithm, right? So the complexity here is easy. So all we need to do is analyze to see how well we did. We want to say, well, you know, in some sense, first we first want to think about how well we could do, okay? Like how well we could do, and then we want to say we did that well, maybe. That's one way to analyze things, okay? How many iterations? So this is the notion of how well could we do. Let's just assume that there is a set cover of size k. So before we decide analyzing this algorithm, it sort of depends on the set of on the problem you got on the problem instance, right? Some problem instances you have to use a lot of sets, some you have to use few. So let's just say you have an instance where you know there exists a set. Just as for analytical purposes, let's just say the optimal, the best solution only uses k sets. Okay, does that make sense? So already you can say, okay, well, that gives me something to work with. Like, for example, if I have 100 items and I know I need at least 10 sets to cover it all, or I know there is a set cover of the 100 items of 10 sets, what do I know about at least one of the sets? How big is one of the sets, right? We're trying to, in some sense, the first line says, pick the set with the largest number of items. So let's try to instantiate that. What's the largest number of items? Do I know something about the largest number of items? If I say the set cover, I have a set cover of size 10, at least, and say the total number of items is n, so just to make it a variable, but you're right, 10. So it's n over 10. Right? So already, once you assume this, now you can start some analysis. Right? Once you start saying the optimal takes this long, or there is a solution that's this good. Okay, so that says a set contains 1 over k of the remaining items. And this is true inductively. No matter where you are in the algorithm, you know there exists a set, Si, which covers 1 over k of the remaining elements. Right? Because no matter where you are in the algorithm, you can choose the 10 sets. You can think about the 10 sets that you originally, say you didn't choose any of them. Those 10 sets do cover the remaining items because they covered all the items. Okay? So it says that there exists one set that contains 1 over k of the remaining items. Okay? Okay, so now we can do some analysis. So let's just put symbols to all the moving parts here. Nt is a number of elements that remain at time t. So nt elements remain at time t after using t sets. Okay? So in iteration t, what we do is we cover at least 1 over k of the remaining elements. So 1 over nt is remaining, so nt over k of the remaining elements are in that, we have a set whose size is at least that big, so we're choosing the biggest one, so we choose a set that will, cover that fraction. Okay, so NT plus 1 is less than what? Well, it's less than NT minus whatever you've covered. Now, it might be smaller. It might be much smaller. But we know the largest it could be is this, because we cover at least 1 over k of the remaining elements, right? So the number of elements that are left to cover is smaller. Okay? Okay. Well, we can do this factoring out bit, right? I'm just factoring out the NT, n sub t. So now I can do induction and go back to the 0th step, right? Every time I'm multiplying by 1 minus 1 over k, it's an upper bound. So every time I know my upper bound is going down, it's a safe upper bound, right? If you use a larger number here, this is going to be only larger. So at the end, we have an induction that says, at the tth iteration, the number of elements I have is the number of elements I started with times 1 minus 1 over k to the t. Okay, when do we stop? When is this algorithm over? We have the beauty of integers, or natural numbers even, right? Once we get to one element, there's one set that covers it, and you're done. Okay? So we stop. As usual, it's like the base case in a recursive algorithm, but we stop when nt is less than or equal to 1. When our nt is never less, at some point, this upper bound, we stop when this upper bound is less than or equal to 1. Okay, that's what we're going to do. We definitely stop when the number of remaining elements is less than 1. It's 0, you stop. So now when your upper bound is less than 1, that means you're done. So what we're trying to do is we're trying to figure out when this upper bound on the right is less than 1. Okay? For what t must this be true? Okay, so I'll let you talk to your neighbor, I guess. What do you think? Any idea how to analyze this expression? Okay. Do you any idea how to analyze this? Now that you know the answer, any idea how to analyze this expression? Yeah. Okay. Okay, so what we're going to do is we're going to plug in t. We're going to just check it. We'll check it. That's one way to analyze it, because I told you in the answer. When you tell me the answer, when I tell you the answer, I can analyze it. Yeah. Yeah. Yeah, there is. Well, we'll get to that. He's right. 1 minus 1 over k to the k is roughly e to the minus 1, and it's in particular less than e to the minus 1. That's the approximation. He's saying we'll actually go over it in slightly more detail. But exactly, that's so in more detail. Yeah. So just this is almost a joke, right? I just plug it in and check. Clear. Okay, but okay, I didn't tell the joke. So now let's go through it a little bit more carefully. Of course, you remember that 1 minus x is less than e to the minus x. Yeah, that's a joke. Okay, nobody remembers. I remember. This is the graph. So just to get you, I'm not, somebody came to my office and asked me in this class, am I going to need to know some math facts? Am I going to be, and I'm like, we'll tell you the math facts, and we do. If occasionally we make a mistake and don't tell you the math facts, but it's a very self-contained course, right? Just trust that if you read the material, you should get all of it. It's all there. So it's a little shocking and a little humiliating that it's all there, but it is all there. So in this case, yeah, this is a math fact. Which is clear here. You can prove it in any number of ways. I'm proving it by picture, which is a little bit flaky, but another way to see it from the picture is this line, 1 minus x, has a slope of -1, and the slope for e to the minus x is always greater than -1 when x is positive, and they're equal at that point. Okay, so that's one way. It's a Taylor's. You could use Taylor's. But so what we're going to do is we're going to take this 1 minus 1 over k. We're going to use this inequality, 1 minus x, which is less than e to the minus x. And I'm going to say, I'm just going to replace this expression by e to the minus 1 over k. Okay? And now you get this. This n should have been in both of these. I'll fix that. But the final expression is e to the minus t over k times n. And now when you plug in k ln n, you get a nice clean expression, right? And t is less than e to the minus k ln n. When you divide out by k, you get minus ln n. E to the minus ln n, those are inverses. So you get 1 over n, right? And then that's it. Okay? So it's just a calculation. Okay? Okay, so at that point, after this many iterations, the upper bound is less than 1. Or, maybe one more iteration. We don't care about plus 1 or minus plus 1 here. So after that many iterations, no elements are uncovered. So t is less than or equal to this. Okay, so now what I've done. Okay. So what I've done is I've given all the other greedy algorithms gave you the right answer. This one isn't, right? I said the best answer has size k. Okay, and this particular algorithm is only giving you a solution whose value is k ln n, k log n. Okay, log base e. Okay, so it's not, this greedy algorithm doesn't really work to give you the optimal answer, but it gives you one that's within a log n factor of k. So it's an approximate algorithm. It doesn't really give you the optimal solution. Okay, which it's the best possible, though, in terms of algorithms as far as we know. And let me talk about that. We did not find the optimal solution, right? We're off by a factor of ln n. And now there's always this notion there's always this notion when you have an algorithm. I gave you analysis, and it showed you that we're getting within ln n of the optimal answer, right? But we're not getting the optimal answer. So now there's two questions. Is my analysis bad? Maybe the algorithm is better than my analysis shows, right? I just gave some analysis. Maybe it's better than that, right? It's definitely at least that good. Yeah. Right. Okay. So he has a question about the analysis. Good question. He says, why when you take away a set, when you do one iteration of an algorithm, why does k shouldn't k decrease by 1? Okay. Think about that. You should think hard about this. This is a great question. It's a good way to understand what happened. Why does it not? What is k? K, what he's viewing k as, correctly, is that, in this case, when he thinks of it as decreasing by 1, it's the number of sets you need to cover the remaining elements. Okay? That's what k is in his understanding, and that's a reasonable understanding. K is the number of sets you need to cover the remaining elements. And his argument is that, after one iteration, we've used one of those sets, so the next iteration, there should be k minus 1. That's not his argument. This is me maligning him and saying that's his argument. Okay, but it's a possible argument for that, right? Because you use one of the sets. What's the flaw in that argument? Yeah. Okay, that was a great answer. It was wrong, but that was a great answer. And what was great about it is he started checking himself. Okay? He had some intuition, which is good intuition. Okay, but then he checked himself. He's like, because he tried to make an argument. And then he kind of gave up and said, okay, let's just do that again. Okay, but the first part was great. He was making an argument. Why is that true? it is, there is some notion of not disjoint that's there, but that's not the particular argument. The point is, there's k-sets that we know in the optimal solution there are k-sets, but in this iteration we may not have chosen one of them. We just chose the largest set, which may not be one of the k-sets that cover the remaining elements. Does that make sense? Okay, so if we knew which ones were in the optimal thing, we would just choose one of them and we'd be done. Are we choosing the optimal? Here, this example will actually make it more clear. Okay, so let's think about an instance where you have a whole set and items, and you have a solution where the first half are covered by one set and the second half are covered by another set. So the solution has cost 2, right? There's 2 sets that cover all the items, okay? But what if I have a third set that covers slightly more than half the elements? And in fact, what it covers is it covers half of the first n over 2 elements and half of the second n over 2 elements. So let's just say it ties. And because they tie, we choose this set. Okay? So it covers, so at the beginning I have 2 sets. I have one set that covers the first half of the 2 sets that cover the first half of the elements and cover the second half of the elements. Okay. That was me trying to dance, but I froze. So, okay, so you have 1 through n. So I have a set that covers this half and this half. That's the solution. That's the right solution. But what I do instead is I have one set, the square set, that covers both the first half of this element and the first half of these elements. So the size of this set is greater than n over 2. Okay? So my algorithm chooses this set for some reason. Okay? And now I have another set that covers exactly, let's call this a different shape, that covers the first half of the remaining elements. Okay, well, now this set here covers more elements than either of these 2 sets in my solution, and so on. Right? I can keep doing this, and I get a set like this, and I keep choosing the wrong set, right? Because it's bigger. It's covering more. It's greedy. I'm picking the set that covers more elements, right? And the real solution would have been to notice these 2 completely covered my solution. So if I had a look ahead of 2, if I took a combination of 2 of them, the best 2 to cover the remaining, I would have immediately solved it. But that's not, right? You can make this harder. Okay? So this gives you, so in the end, what happens is how many sets do I use? Well, every time I have, you can actually see the analysis here too. Every time I have the number of remaining elements, so after log n iterations, I'm done. But I could also make it that bad. Okay? So this is a problem, and this is a subtlety in the analysis. Okay? If I did pick one of the sets in at any iteration, I would actually be better. I could get a better analysis. So now the question is, this is greedy. This was the first dumbest thing to possibly do, right? If I was a corporate manager who didn't know anything about tech, he would say, oh, let's just pick the cell tower that covers the most, right? This is the obvious strategy. Is there something more sophisticated, something better we can do? And the answer is probably not. Again, to do better, even this is very, it's not only that we can't find the optimal, we can't even get within a better factor of optimal. Like ln is really the answer, okay? Like this being off by this log factor, you have to be unless p equals np, okay? And this is this notion, we don't have algorithms. P is a set of problems for which we have algorithms in polynomial time. NP is a much bigger class of problems where we don't know any algorithms for these guys. If you can give a better algorithm for this simple problem, you would actually give a better algorithm for all the problems in this class in NP. So we don't know that. We don't know how to do that as humans, as far as I know. And maybe the NSA knows how to do it, but I don't know how to do it. Nobody else knows how to do it, yeah.
So when you're saying that that's optimal solution, is that an assumption you're making?
It's in the analysis, right? It's only in the analysis. He's asking is, why do I get to assume that it takes k sets? Well, k is an integer. So I know the optimal solution is some integer number of sets. So that's why I get to assume it. Okay, so now for chapter 6. Okay, so far what we've done is we looked at divide and conquer. Are there questions about greedy or yeah? Okay, so what's the algorithm? She's asking how this example works. Well, the example is trying to fool the algorithm. Okay, what's the algorithm? Pick the largest set. Okay, so I have an instance, and I'm writing down the optimal solution as this 2 halves, right? So the right thing would be to do is pick these 2 sets and be done with it, okay? But that's not what the algorithm does. It picks the largest set, okay? So now in my instance, I'm adding sets to it to make something to fool my algorithm, okay? And the way I'm doing it to fool the algorithm is I'm taking the first n over 2 items of this set, and the first n over 4 items. So now n over 4 items of this set, and then the first n over 4 items of this set. What is n over 4 plus n over 4? It's n over 2. Okay, so so it's the same size as this set. So I will pick this guy, right? And now what do I do? Now I'm going to try to fool the algorithm again, and I'm going to add another set to my set system. And that will consist of the first n over 8 items of whatever's left of this set, and the first n over 8 items of whatever's left of this set. Okay? And now these 2 sets, now that you removed all these elements, this set only has size n over 4. So n over 8 plus n over 8 is bigger than n over 4. What? Or equal. Equal, bigger or equal to. Same size. That's fine. Yeah, they keep decreasing in size too, because you're evaluating it with respect to the number of remaining elements. Good, 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 good. She's saying, I think the confusion here is that the first sets had n over 2. Once you start using smaller sets, wouldn't you choose them? But you're evaluating it with respect to the number of remaining elements. Okay? That's what it says, right? Because otherwise it makes no sense. Otherwise, you would pick some set that's already covered a lot of elements that you've already covered. It doesn't make any sense to do that, really. Okay? And that algorithm won't work because of P doesn't equal NP as far as we know. So you can try other algorithms, but I promise you they won't work. I mean, I'm very sure of that. Okay. So now the design ideas here, what we've seen so far is divide and conquer, graph exploration, and greedy. So the next 2 are these things. And dynamic programming is, I'm just seeing with the time. Okay, dynamic programming is what we're going to do next. It doesn't really have much to do with programming. It's just a historical name. Okay. The programming they're using there is more like using tables to do stuff, is what they meant in the 50s when they invented this idea. Okay? So let's revisit shortest path on a DAG. Okay? Now, just shortest path on a DAG, we're revisiting this one because really computation is about a DAG. Okay, all the computation in some sense is about a DAG, right? You better use the things you computed before to compute whatever you're computing now. Okay, so in some sense, a DAG is a very general representation of computation. Okay, so let's look at this particular computation. How do you compute this thing on this DAG? Okay, so what you do is, okay, so the distance to D is has a very nice structure, right? You know, no matter what, to get to D, you have to get to A or you have to get to B for path problems. That's the only choice. Either you have to get to A or you have to get to B. Okay, now if you want to find the shortest distance to D, in this case, there's only one way to get to A, but of all the ways to get to A, if you're going to go through A, which way should you choose? The best way, right? If you want to get to D, and you know you're going to go through A, you should choose the best way to get to A, the shortest way to get to A. Does that make sense? It's sort of, I'm saying something that's so obvious, but it's very powerful. So when I say the shortest way to get to A, that's encoded in the distance A, in this expression distance A. It says the distance to D is actually a function of sort of the exact same problem for A. Okay? So it's like recursion, right? You can think of this as a recursive algorithm. The distance to D is a recursive. You're writing a function. You just take the minimum of a function that calls the distance to B and adds 1. Or the distance to A, it should be distance to B and adds 4. And the distance to A and adding 1. Okay, that's it. It's really like just to compute this thing, you can think of it that way. Right? It's just a recursive call to the previous guys. Now, in some sense, it's slightly funny because if it wasn't a DAG, the distance to A may go through D. But in this case, we don't know. We know the recursive call to the distance of A doesn't need to consider paths that go through D. So there's a lot of information in this little statement. Okay? It's a recursive call. A is sort of before it in the topological order. You know that the solution for computing distance to A doesn't involve D at all, right? You don't want things to call each other in these recursions because then you run out of stack, and it's an infinite loop. So distance of U can be computed with the distance to the tails of the incoming arcs. That's the idea here. Okay, so the answer is then you linearize the DAG. And now you see that for D, here you see more clearly that for A, the solution for A doesn't depend on the solution for C or D or anything. Right? It only depends on the solution for nodes before it. Okay? So you can compute the distance in order. Okay, when you reach a node U, the tails of the incoming, and when you come here, if you go in order, what can you do? I can compute the distance at S, which is what? Yeah, and then the distance to B, which is 1. This is 3. This is, now with C, it's 6. With D, A is 2. This is 5, and so on. Right? You just need to look at the 2 inputs that come before you. I only looked at 1 here. Okay? And so, okay, so then that's sort of a review of what happened. But I'm sort of looking at it as sort of procedure calls and making sure those procedure calls aren't calling each other. Making it into a DAG is essentially just a way of making sure these procedure calls don't recursively call each other. Okay? Okay, this is the algorithm in linearized order. You do this. You solve all the subproblems of the form distance to V. So our algorithm is we really wanted to find the distance, just say maybe to T, but instead we find distances to everybody. Okay, so we kind of, it could seem harder because I may have only wanted the shortest distance from S to T, but I computed everything else. Okay, so I computed all these other subproblems. Okay, and we progressed to sort of larger subproblems. So it's, you can think of, right? And the basic thing, if the shortest path to B goes through C, you might as well use the shortest path to C. So the subproblems have the exact same flavor. It's recursive. Shortest path to B, shortest path to C. Okay? So sometimes they call this optimal substructure. This works for finding longest path, the product, or path lengths, or any number of things. It's a DAG. It's very general. It's like all computation, in a sense. Okay? It is all computation. Okay. So let's just think about longest path. What do I need to do to change this to longest path? Yeah, it's that easy. It's as trivial as you think it is here. Okay? The longest path to B, if it goes through C, I might as well use the longest path to C. Right? So the recursive structure stays the same. Okay? Okay. So dynamic programming is sort of solving the sequence of subproblems and solve them in order. That's sort of a general view of what's always going to happen. There's always a DAG view that you can take of these algorithms. I'll present them usually. Okay. Okay, so now here's the first one. Given a sequence of numbers, A1 through AN, I want to find the longest increasing sequence of numbers, subsequence. Okay, so here, here's a sequence of numbers. A1 is 7, A2 is 3, A3 is 5. So I want to find a subsequence of this of these numbers, which when you read them from left to right, that subsequence keeps going up. So for example, if I just choose the first two numbers, 7, 3, is that an increasing subsequence? No, because 3 is less than 7. How about 3, 5? Is that an increasing subsequence? Okay. How about the 1 and the 9? Is that a increasing subsequence? Yes, because they don't have to be adjacent. Okay, so I don't know what's the longest one here is. What is the longest one, you think? You guys see the longest one? 3, 5, 6, 9. Yeah, 3, 5, 6, 9 looks pretty long. It's 4. 1, 2, 4, 8. That seems long. Okay? So let's try greedy. So here's two options for the greedy. Right? Now we just learned about greedy. Let's see why we're not doing greedy. Because the answer will be that neither of these work. But let's choose the first number in the list. That's greedy. Let's just start with A1 and just pick the next number that's higher and the next number that's higher and the next number that's higher. Right? Okay. A is bad. It's clearly bad. Right? Why is it bad? Yeah, what if the biggest number is at the beginning of your list and then it's completely sorted? That's a bad. Okay. So, and here you see it produces 2, which is also bad. Okay, so you can try method 2. Here it works on this example, right? But I think this is the best solution here. But obviously it doesn't work if you put the lowest number at the end, right? So these are, like, when I do this, it's really what you should do when you're, like, have an idea about an algorithm. Is like, let's try to see what breaks it. Let me alternately try to prove that it works, and then when you can't get a statement that makes sense, maybe there's an example that shows that statement doesn't make sense. Okay? So what do we do now? So how do we proceed? What's the right thing to do here? Yeah, there's some DAG, right? I mean, I drew arcs on purpose here. Okay? Those arcs kind of have meaning. The arc is that 1 is less than 2, and so I'm drawing an arc from 1 to 2 here. And in the solution, that's what has to happen. These arcs have to be there between subsequent elements, and they should be the longest sequence of such arcs, right? Okay. Did I say that out loud? Did I say the longest sequence of such arcs? So what should I do? They go from lower to higher. Well, let's put in all these arcs, right? Is 5 less than 6? Yeah, let's put in that arc too. Let's make a DAG here where we just say we just put in all these arcs that could be in our solution, right? These are parts of our solution, right? Okay. So the solution is a DAG. You add more arcs. 7 is less than 8. 7 is less than 9. 2 is less than 4 and less than 9. 2 is less than 3. That's written in red because that's bad. What's wrong with that? 2 is less than 3. Yeah. It also needs to be before it in the sequence, right? That's not what longest increase means from left to right. So then you can put in all the arcs, right? The arc from 9 to 4 is not there, then the arc from 9 to 1 is not there, you see? And now the question is, it's a DAG. The longest increasing sequence is exactly A or B. Right. Right? And we just talked about how to do that. Okay? Any path is an increasing subsequence. Any increasing subsequence is a path in the DAG. Right? So this is the algorithm. It's really just longest path in a DAG for this particular solution. Okay, let's analyze it a little bit. First, we build the DAG, and then find the longest path. Okay, so building the DAG could take O of n squared time, right? Because you're comparing every pair of elements and deciding whether to put the arc from left to right. Okay, and solve. Now, solving it is efficient because remember, finding the longest path in a DAG was O of m time, or you have to look no further than every node processes all the incoming arcs. That's all the work that's done. Okay, so it's the size of the DAG. Okay, it also takes n squared space because you have to put in all these arcs. Okay, so now the question is, can you do better? You see a way to do better? Should I go through and build this DAG and then solve this problem? Well, I don't really know how to do better than in time, okay? But I know how to at least use less space. So let me show you that. Okay. Okay. So okay. So we're going to implicitly use the DAG. We're not going to write down all the edges. We're going to still do all the comparisons, but we're not going to write down all the edges. Okay. So now we're going to think of it as a recursive procedure. So L of I is a function of I for our instance. Okay? And L of I is the length of the longest increasing subsequence ending at position I. Okay. Okay, and so now, well, actually, I guess I'm thinking of it as a table entry here. So now, for I equals 1 to n, the longest subsequence for I is 1. Okay, the first statement says, before I've done anything, I could just think of myself as a subsequence. The length of myself as a subsequence is 1, right? So the longest subsequence ending at I. So one option, the longest subsequence at I is I could be the maximum number in the list. So there's a subsequence of size 1 there. So that's what this first initialization is. Okay? And now, for all the previous guys, I look and see if A sub j is less than A sub I. That's testing if this arc is there. And if so, I can add myself to the end of that longest subsequence. So that's what this particular instruction is doing. It's saying L of I is max of whatever I thought it was before. And initially, it's just me, my sequence just starting it with me. Now, if I have somebody who's less than me before that, my longest subsequence is the largest of whatever I thought before, and the sum of that guy's subsequence length plus one more, me. Okay? That's what it's saying. The max is what I thought before plus me. Okay? Largest Li is the length of the longest subsequence. It's O of n squared time still, because there's the O of n squared time you see in the two loops. The first one goes up to n. The second one goes up on average up to n over 2. Okay. So on average, to n over 2. But it could go up, whatever. It's roughly O of n. Okay, and the space is O of n. The space here is the space that I use is this array that holds all these L values. Right? And I have one L value for each item. Okay, so this doesn't find it. This doesn't find the longest subsequence. What does it find? Yeah, the length. Okay, you can do something to. If this thing fires off, you just say, well, I use A sub I, And the one before it, I use a sub j, then I follow its pointer. Okay. Okay, so I chase previous pointers to find the solution. Okay, does that make sense? We also sort of did this, we had the same issue when we had shortest path trees, right? We usually were just computing distances. We didn't think about what the tree was. Okay? That's just something recoverable using pointers. Okay, any questions? Okay. Okay, define a set of subproblems, order them so each subproblem can be solved using solutions to previous subproblems. Longest increasing subsequence, what we will say, what you will hear, what you will be annoyed by when you come into office hours every day for the next 2 weeks, if you do, is what is a subproblem? Okay, so this is the key to dynamic programming. What are the problems? What are the subproblems? Okay, and here the subproblem is we wanted to find the longest increasing subsequence in the whole series, in the whole sequence, and the subproblems is we just try to find the longest increasing subsequence up to some point in the series for all those points. So there's a bunch of subproblems. Okay, and we only need L sub j. Now to solve, the next step after you define the subproblem is to say, well, how do I solve L sub I using smaller subproblems? And here the smaller, what smaller means is j is just smaller. Different ways of defining these things, smaller is going to show up a little differently. Okay? So I can solve the problem for L sub I using only solutions to problems where this j is less than I. So they're smaller. Okay? So it's a DAG of problems to solve. Okay, and one other way, you've seen this before, and I told you at the beginning, and I want to remind you again, because this is also a nice way to view it. Only need L sub j for j is less than I to find L sub I. That's the key. That's this sort of basic problem. It's a very simple problem. I'm sorry to go at length at this, but I've seen the confusion many a time. So understanding it in the context of the simple problem is very important. Okay, so recursion, does it equal dynamic programming? Subproblems and solutions, right? Isn't this what recursion is? You call the same function on a smaller subproblem, built from smaller subproblems. So we could have done all this. It sounds so much like recursion. We might as well write the code. Okay? So that's what I'm doing. I'm writing the code. So now, instead of thinking of L of I as an array entry, I think of it as a subroutine call. Okay? And now, when I do this, this is not an array entry. This is a subroutine call. And I should probably have stored this in a value to save it, so I didn't make the call twice. But OK. So, but it's not going to matter for a reason. The problem with this is the problem with thinking about it recursively is it's a disaster. OK. This subroutine call will make every possible subroutine call every time, right? It's going to go all the ways back to the beginning. It'll enumerate all the paths in the DAG. Okay, and there's an exponential number of paths in the DAG. But I can save it. And I can save this algorithm so it works just fine. Okay? It's called memoization. Okay, what's a poll? Who knows what a functional program is? Okay, so used to be when they taught 61A with scheme like it was intended to be taught. Okay. Everybody would know. And it's not your fault. I'm sorry you went through a broken educational system. Oh. No, I'm kidding. 61A is clearly amazing. But this particular detail is really an issue. And the issue is the following. You're allowed to, what can you do with this program to make it fast? How can you what is memoization? Yeah, what you could do at the very beginning of you can add a line to the beginning that says, if I was called, look up in a hash table, a global hash table, right? We'll put it in a class so you don't get points off. on your code. But a global hash table that says, was this called before on I? If it was, I'm going to return the value I computed before. Okay? And what is that? That's exactly a table entry. That's exactly what a table entry is, right? So writing down this thing all in an array is exactly the same thing. Okay? So it is the same thing, and basically, if something is functional, in this case, in the context of the instance that we were given, this is a functional call, meaning that the next time you call it, you can get the exact same value back. So that's what functional means. It's a function of the input. Now, regular programs are not functional, and why is that? Yeah, side effects, right? So in Python, immediately you can sit there and say A equals 3. So it's really hard mentally to understand what functional is when they allow you to do assignment right up front. In Scheme, you're not allowed to do that, so you have to program functionally for a while before they introduce side effects, and you're really annoyed. It's the most annoying thing in the world to program this way. Until you've done it for a few weeks, and then they give you side effects, you're like, no. Please, no, because once you have side effects, you don't understand anything. So that's when the bugs happen, and that's what you see when you're in your debugger late at night. I guarantee you it's because of these side effects. So anyway, that's a tangent, but okay. But it's very important. In this context, the li answer is the same each time, so you just remember and return. You don't have to make the functional calls, the subroutine calls. Okay? And only n different arguments provided to L. Each call takes order n time the first time. So it's the same as iterative. Okay? So it's the same as, and this is exactly the same thing that fixes fib. You can write Fibonacci recursively as long as you're writing it, as long as the programmer, as long as the compiler understands this is a functional program, it would actually run fast. It doesn't go slow. Okay? Okay, good. Okay, so I'm going to give you a little break, and then we can begin. Yeah. Okay. Okay, so now I'm going to give you a fairly sophisticated. I'm going to give you a more sophisticated algorithm to show that there's actually some work to do here. Okay. So spell correction is thereafter versus thereafter. Let me see if I can get this. Okay. Okay, so in spell correction, you may want to, well, I clearly meant thereafter, right? Does that make sense? When I typed the thing on the left, I meant the thing on the right. Is that fine? Okay, so in some sense, what is the problem of spell correction? It's to find the closest real word. Okay? Given two words, how far apart are they? How do you even decide how far apart they are? I can't see you. Okay, so it's the best alignment. So what I'm going to do is do this. I'm going to write it out like this and say, okay, so I'm going to write it where the whatever's on the top and whatever's on the bottom, they're sort of lined up. T and T is lined up, H and H is lined up, E and E is lined up. A and this thing on the bottom, which is called a gap, those are different, the A and the gap character. So I'm going to count that as 1. And then the R and R are lined up in the same, so I count that as 0. So this is the cost. I'm just going to define the cost. So the cost for T and T is 0. The cost for H and H is 0. E and E is 0. A and gap is 1. R and R is 0. Gap and E is 1. Okay? So and so on. And everything else, all the characters line up and are the same. So I could say the cost is 3. Okay? So that's what I'm going to define. My distance between words is how different they are. This is how I'm defining it. Okay? So the edit distance, it's also called the edit distance because this alignment shows you how to change one word into the other. Okay? It uses 1 deletion and 2 insertions. So what I'm going to do is try to change the top word into the bottom word. And so what I'm doing is, I look at the T, and I see in the bottom it's a T. Okay, yeah. So this says, okay, so that's the next slide. That was funny. Okay, nicely done. Okay. It's distracting, but it was funny. So you start with this one. You can delete at position 4 and you get something else, right? You get something smaller. Then you can add E, okay, and then you add an A, right? So it costs 3. 1 deletion and 2 insertions, okay? So 3 steps. And you can read these operations off to alignment. The first one is what I did is I looked at the top one. I'm trying to convert the top one into the bottom one. And I see T is T, H is H, E is E, nothing to do. A is gap, so I should delete the A. That's what the instructions are telling me from the alignment. Okay? And I see a gap in the top one, and I see the E, and it says insert the E. Okay? Does that make sense? So this alignment tells me how to edit. Right? You can translate it straight off. You can read it off. If there's a gap if the characters are different, it's a substitution. You change the character. That costs 1. If the characters are the same, it doesn't cost anything. You don't have to change anything. If there's a character to a gap, you're deleting. If there's a gap to a character, you're adding. Okay, so there you can actually have another alignment. So this is a different alignment. So this seems also the same. TT is the same. HH is the same. EE is the same. EA is different. So I could have used a substitution instead of a deletion or an insertion. Okay? So the cost of this alignment is also 3 because there's 3 different characters that are aligned on top of each other. Okay? Okay, 2 substitutions and 1 insertion. So you can just see that it's spelled out. Okay, I guess you can see I don't know whether this is interesting, but how do you spell it? Oh. Okay. The problem is I can't remember. Okay. There, F-T-E-R. Okay. Oh, theater. Okay, but the second one is thereafter, apparently. Okay, so you can see that it works, sort of, yeah. So I didn't choose the right character. Okay, yeah, though. Okay, Homer was here. Theater is the right, yeah, I knew it was theater. But, okay, so do you see the idea that it's really doing this, right? The second closest word was thereafter. We think it's thereafter because there's some other algorithm we're using than edit distance, right? Theater only has cost 2, right? This is the theater thereafter to theater. You see there's only 2 differences, okay? So they chose the closest word. Okay, so now what is the problem? How do you set up the problem? Okay, so I went through at length through this alignment because like the prefix-free codes, this alignment will help us come up with an algorithm. Okay, it just organizes our thinking on how to piece together subproblems. Okay, so what our input is a string, 2 strings, x and y. X has m characters, y has n characters, and we want to compute the best edit sequence from one to the other. Okay, or the best alignment from one to the other. Okay, sometimes it's just nicer to work with alignment sometimes. Okay, so you find the edit distance between x and y. What are the subproblems? Okay, well, how about the edit distance between x up to I and y up to I? How about using that as a problem, subproblems? Okay? So in some sense, you know, you want to align the first part of the strings before you align the whole string. Maybe though that's a reasonable thing for the subproblems. Okay? So in some sense, okay, so the alignment is fixed. The problem was this is stupid, okay? It's really not good because if you think about alignment, you're saying the first I characters align with the first I characters recursively. So the only thing you can do is substitutions. You're not allowing gaps to appear, right? This particular thing is stating, you're coding into your subproblem that you can only do substitutions and additions at the end. Because you're saying the first I characters have to align recursively, and the first I minus 1 characters have to align. Okay, so this is just wrong, right? It doesn't work, right? So they have to align. This is the only solution you're going to find. Okay, so that doesn't work. Now you have to, the point is you have to search over different alignments. You have to say, maybe my first I characters in X line up with the first J characters in Y. You have to consider that possibility, right? These alignments are really about trying to figure out which subset of characters are here in the first one and which subset are there, or which sub-prefix. Okay? So you have to search over all these alignments, all these possible alignments. Okay? Right? Here, the first 5 characters we're trying to find the best way to line up the first 5 characters against the first 4 characters of the second one. Okay? So and when we do that, I'm going to say a priori, look, I don't care what you do. Just give me the best way to do this. I mean, here you see the answer, but say you don't see the answer. I just recursively want to know the best way to do this, to continue from. I don't want a bad way to do this. I want the best way. This is one way. Maybe there's a different way, but I don't want the bad ones, right? Okay. So I should choose the best such mapping. So this is this optimal substructure. I keep saying best because I want recursively the best, right? Okay. Okay. So, so this is the edit distance. So the subproblems I want is the best way to line up the first I characters of X with the first I, J characters of Y. Okay? Those are, and I originally had this nice, easy problem, just line up this whole big string. But the way I'm going to solve that big problem is all the possible ways to choose I and J, use those solutions to piece together. And hopefully what should happen is once I have one of these, I should be able to build up the solutions for these things from smaller I's and J's. Right? Okay. Okay, so edit distance X, so this is a subproblem. And I'm going to represent again, you can think of E of ij as a subroutine call or a table entry. Okay? It's the edit distance of X, and these subroutine calls explicitly have X and Y in their environment, right? So you're explicitly using those specific strings. Okay? So how do you compute E of ij? Okay. So what I've done is now I've defined, I had one problem, now you have a lot of problems. You know, the roof is leaking and no, but never mind. Okay, but what you do is you get to use the smaller problems to build solutions for the bigger problems. Okay? So you get to use the solutions of the other subproblems. Okay? So this is how we do it. Okay? So you look at any aligned positions in a possible solution. Okay, so now I'm thinking of what a solution looks like. And now, if there was an insertion at this place, if you're lining up, okay, we're thinking of lining up the string up to I for X and up to J for Y. Now the last position could look like this. Y sub J could be here, and there could be a gap up there. Okay? Or, which corresponds to an insertion, right? You're inserting a character into X. Okay, here, the other last position, right? What I'm saying is I'm just looking at a place here. So maybe the first 4 characters in X and the first 4 characters in Y, it would be A would be here, and a gap would be here. First 3 characters in Y. Okay, or they could be over each other, as is the case here, right? F and E are over each other and they're different, or the same. Or they could be over each other and they could be the same. Okay, so those are the possible ends of your alignment. Okay, when you're done aligning the first I characters of X and the first J characters of Y, you have 3 cases. Either you have a gap in Y sub J, you have either X sub I and the gap, or you have x sub I and y sub j. Okay, in the alignment, right? You have two positions you're looking at in the last position. Okay, so in some sense, what could be, after you've done this, in this case, what you have here is you say, okay, I'm stripping off a character of y. And now for the rest of the alignment before it, what I want is the best alignment of I to j minus 1. Right? In this case, I want the best alignment of I minus 1 to j before. And here, I want the best alignment of I minus 1, j minus 1. Okay? So this is what it says. If I'm looking at the first 6 characters of x and the first 4 characters of y, I want, in this case, what is the cost of this in my alignment? 1. What's the cost of this in my alignment? 1. What's the cost of this one? It depends on whether xi or yj are different or not. Okay? So now here, if you look at the first 6 characters of x, you get up to the arf, f as the last character. And the first 4 characters of y, and the last character is r, right? R and f are different. Okay? So the 3 cases here are, in the first case, you strip off y, and you look at the recursively best solution for 6, matching the first 6 characters of x to the first 3 characters of y. And then you add 1 because this cost you 1 in the alignment. This is why I went over the cost so carefully. Okay, and this cost you 1. That's this case. You're stripping off a character of x and then finding the best solution for matching the first 5 characters of x with the first 4 characters of y, and then adding 1. And then you're stripping off both of these characters and trying to find the best sub-solution before that, and adding 1 because these 2 characters, f and r, are different. Okay? For 3-3, you can do the same exercise. In this case, the difference here between this and this is that you have a +1 here. Here you don't have a +1 because at position 3 in both of these strings, you have an e. Okay? And so this one doesn't cost you anything. So you don't have the +1 in this case. Okay? Okay. Okay, so this is a whole solution now. If xi is not equal to y, you use this first case, right? You say it's the best of aligning you strip off one of the characters of x in the first place, and you add a gap, which costs 1. You strip off the last character of y in this case, you add a 1 for the gap, that's an insertion. And the last one is a substitution. Okay? And there's no, if the last 2 characters are the same, the substitution is fine. Okay? Okay. Okay, so now you have to do the base cases. I of 0 to j, what should that be? Oh yeah, I was being rude. Okay, so what does that mean? Go back and look at the subproblems. What does that mean? You're matching the first 0 characters of x with the first j characters of y, meaning you better insert all the characters of y. That's all you could do, which costs j. Okay? What about here? Here you're matching the first I characters of x to the first 0 characters of y. You're trying to rewrite it that way. So therefore, you better delete all the characters of y. Yeah. Well, you're going from x to y, so you're inserting. Oh no, here you're deleting. Here you're adding. You're right. You're inserting here. Here you're inserting. There you're deleting the characters of x. This is not a recursive call. This is just an initialization. For this recurrence? Yeah, well, let's talk about that after. Okay, I thought I explained it before, but let me. Anyway, here's all the code. It's the same thing. So, and I'll show you in a minute. Actually, the example will make it clear. Okay, so, okay, what's the time? Well, it's 2 loops, right? N times M, right? This is easy. Okay, the inner side of the loop is a minimum of 3 expressions. Okay? Okay, so now you can see an example. So right now, this is the cost of matching the empty string, rewriting the empty string into that string on the top. Here, you're trying to figure out the t. So you're matching t. In this one, you're matching t to th. Okay? And it costs you 1 because you have to do an insert for h. Right? To get to t to the, that's the second character, you have to do two inserts, right? And the key here is that what you do to figure this out, to get that 1, what you do is you look up at the 2, you look over at the 1 diagonally, and the 1, and you look over to 0. So what you look at is for example, in this case, what you look at is that t blank, that's the one on the left. Okay, this one here, it corresponds to this. So this guy, what he's doing is the best option of adding another character, which is taking this solution and adding a character, or comparing these 2 characters, which would be taking this solution and adding 1 because these 2 characters are different, or deleting a character, which is this one. Okay? So each one of those, this number comes from looking from these 3 table entries. Yeah. Yeah, so she asked what's the DAG look like. Okay, so the DAG looks like this, okay? So it looks like you look at that big table entry. So I'll let you go through this example, but it's at home. It's kind of long. But the DAG looks like this. So this guy, what does he need to compute? He needs to know you're matching the first I characters to the first J characters. You need to know the best way to match the first I characters to the first J minus 1. It could be that's the best way to do it. Or it could be that you need the solution for matching the first I minus 1 characters to the first J minus 1 characters. Or matching the first I minus 1 characters of X to the first J characters of Y. Okay? And those are those 3 cases. One is a dash character, one is a character dash, and one is a character character. The diagonal is a character character. Right? Okay, and then the number of nodes in this graph is order nm. The number of edges is order 1 per node. Okay? And that's it. So, yeah. But